everybody. My name is Giancarlo Flores. I'm the chair of the Department of Civil Engineering, and thank you very much for joining us today to this special seminar on civil engineering. We do have today Dr. Houtuo Tiom Pue. Dr. Pue, a dear friend of mine, is a senior lecturer at the River Engineering and Urban Drainage Research Center at the University of Malaysia, in Malaysia. He obtained his PhD and master's degree from Kyoto University in Japan, and his bachelor's degree in Malaysia at University of Science Malaysia. And he has specialized as a civil engineer on research focusing on the mathematical and numerical modeling of open channel hydraulics. He teaches both at the Department of Civil Engineering, and he's also involved in consultation projects throughout the country. And he has received an transdisciplinary research grant for the development of numerical models for mud flow disasters, and the fundamental research grant scheme to study the formation of pool and riffle structures in rivers from Malaysia. Dr. Pue has a long experience with hydraulics and water resources. He has worked for a very long time on this topic, and I'm really happy that we have him today. He's going to share with us some of the results of his research, his work on the development of a numerical model for the simulation of tsunami wave propagation on land. As you know, we live in a country prone to earthquakes and tsunami disasters because we're part of the Pacific Ring of Fire. And understanding, being able to predict the behavior of these tsunami waves as they reach land, it's a problem that we should address. We should be able to understand, we should be able to predict, so as to precisely create ways for these same structures to avoid disaster in a resilient way in the future. So without wanting to keep him from sharing his work, Dr. Pue, thank you very much for joining us today, and we can start your presentation. Yes, we cannot see you, if you can.
Oh, you need my video, yeah?
Of course.
Okay. Okay, can you see me now?
Perfect. Okay, I'm going to shut down mine. Thank you.
Thank you. So, good evening to all the participants in Peru, and good morning to participants from Malaysia. It is 8 o'clock in the morning in Malaysia. So I've been working in Kyoto University together with Professor Flores. First of all, I would like to thank Professor Flores to for inviting me to this webinar. Today, I'm going to talk about the development of a numerical model that we made in University Science Malaysia. Oh, but by the way, I'm from the River Engineering and Urban Drainage Research Center in the University Science of Malaysia. And the development of this model is for the simulation of tsunami propagation on land. So I did a very rough survey on site in the internet, and I found that Peru has recorded 23 tidal waves since 1586, with about 6,000 people died. Compared to Malaysia, we are actually very safe from seismic activity, but still we got 2 tidal waves since 1674, and mostly are from the Indian Ocean tsunami, the Aceh tsunami, that occurred in 2004, with 137 people died, with a mean wave height of 3 meters. By the way, we are really far away, so far that I couldn't zoom out. I couldn't fit Lima and Kuala Lumpur, almost couldn't fit Lima and Kuala Lumpur on the same screen. This is the best shot that I could get from a screenshot that I could get from Google Maps. So we are really far. It would take about 1 day and 6 hours to fly from Lima to Kuala Lumpur. This is a photo of the after the tsunami incident in one of the coastal area in Malaysia in 2004 due to the Indian Ocean tsunami. So many coastal houses were destroyed by the inland propagation of tsunami. So in Malaysia, we have a lot of what they call fishermen villages along the coastal area, and most of these houses are built are wooden houses, but some of the houses are built using bricks as well. However, those houses, those brick houses, also succumb to the force, the hydrodynamic force of tsunami. So this is the recent photo that I took from the Memorial Museum, the Tsunami Memorial Museum in one of the states in Malaysia. You can see that even the brick walls are destroyed by the tsunami wave. Of course, there's no more roof. All are destroyed by the tsunami wave propagating on land. So motivated by that, we decided to build a numerical model to improve the design of the houses in the coastal area in Malaysia. So we came up with an idea to develop an in-house numerical model. Of course, we can use what we call commercial model like Fluent or Flow3D, but it is very costly to buy those software, especially with, if all the students wants to use that software, they have to wait because of the number of license. So therefore, we decided to develop a model for our own. And in this model, we face a few challenges in developing this model. And I would like to share with you the challenges in developing the model, and also the methods that we use to develop the model and the performance of our model. So the first challenge is, of course, this challenge is also a general one. So the difficulty to represent free surface. So what does it mean by free surface? Free surface is the interface between air and water. It can be also between two different fluids of different density. So I would like to show you the evolution of the free surface in this dam break problem. This is a dam break problem where we release a finite amount of water into a smooth bed. So when I play this video, you can see the deformation, the complex deformation of the water's surface. So it is quite difficult to model accurately this complex deformation. So here we have three models here. The first one is by using commercial model, Flow3D. The second one is the model that we developed. And the third one is also a model that we developed, but it's very primitive model. It's called the marker and cell. So you can see three different performance of this model compared to this experiment. This experiment is carried out by a researcher from Russia, Lebowski. Later I will share with you the reference. Okay, apart from the surface configuration, we do have a few parameters to judge the performance of the model based on this dam break flow problem. I will show I will show in my next slide how we measure this, how we use this dam break flow problem to gauge the performance of our model later in my presentation. So we also have a different type of modeling for surface flow. This is totally another type, is based on Lagrangian method where we trace all the particles. So just to show you a sample, this is a dam break flow for very high viscosity fluid. You can see that the fluid is slowing down and it has a very round front here. So this kind of model is also widely used to study tsunami propagation. In fact, one of the famous laboratory that is doing this MPS model is in Kyoto University. The volume of fluid, I would like to introduce to you a method called the volume of fluid. This is one of the most widely used method to represent the interface between water and air, or between two fluids. Okay, I'll explain very in general. So if we have two fluids, we want to trace the interface. This is the interface of between these two fluids, fluid 1 and fluid 2. So we give a function f. The function f will have the value of, let's say we want to trace, we will choose either of the fluid. Okay, we want to track the movement of fluid 1. If the mesh, or if the calculation cell is full of fluid, then we give a value of 1 to the function f. On the other hand, if the cell doesn't contain fluid 1, it contains another fluid, so the value of f is 0. So those cells that contains partially filled will, with fluid 1 will have a value between 0 and 1. For example, f equals to 0.5. That means 50% of this cell is filled by fluid 1 and 50% are fluid 2. So we have the value of 0.5 for f function. So what we do is this, after solving the velocity field, we use the velocity to move this function so that the new configuration, the new interface can be built, can be constructed. And this, in order to in order to move this function, we use the advection equation in this form. The next challenge is, how are we going to solve this equation? Of course, it looks quite easy to solve, but the accuracy of the advection equation solver is very critical in order to get a good result, in order to get an accurate surface configuration, surface deformation. So I'll give you an example. I'm going to show you the result of solving this advection equation. This is a 2D advection equation where rectangular cubes are going to be advected in a circular motion. Okay, this is two model solving this advection equation, and we use what we call a step function. It looks like a box here. We are going to advect in a circular motion. So by right, if this is solved exactly analytically, this box should move in circular motion without any changes in their shape. It's going to be a box moving around. But if the method used is not good, it's not accurate, you will see that the box cannot be advected accurately. So I will show you the results. On the left-hand side, we have the first order upwind scheme, which is the easiest method to solve this equation. You can see that the shape of the box has totally gone, not even one rotation. Okay, the accuracy is very, very low, and you can see diffusion. You see diffusion of the shape. You can see some of the values are spread around the shape. Compared to another model, which I use the CIP CSL3 scheme, the shape is pretty much conserved. Okay, the maximum height of 1 is pretty much conserved, and the shape is pretty much conserved, the square shape. Although it is not perfect, but this is just to demonstrate to you that the quality of the solver, advection solver, is really important in developing what you call a hydrodynamic model with free surface. Also, if we use a very low accuracy model, you will have a problem, what we call the smearing of the interface. So if we zoom into, this is an example, just an example, an image I took from Flow3D. So the region where, if you zoom in, the region close to the interface will have some smearing. Okay, so these are the interface between two fluids. Okay, this is a zoom in from this section. You can see there is a very slight smearing here. So the better the scheme, the less the smearing of the surface. Therefore, the configuration of the surface is more accurate. So we call this, we want to get a sharp interface between two fluids. So the sharpness of the interface really depends on the accuracy of the advection solver. Of course, it's not only the advection of the function f. This advection equation is also contained in the momentum equation. As you know, momentum equation is the governing equation for the motion of fluid. So if we cannot solve the advection equation, here I cast it in the red box, if we cannot solve this accurately, the accuracy of the model will be very low. So therefore, the focus is on, the difficulty is on solving the advection equation accurately. And the third difficulty is the maintaining the conservative property of a model. So what does it mean by conservative property? Imagine we have a dam break flow like this, okay? So when we start the problem, we have a finite volume. We know the volume in the domain, and this volume must be always conserved based on the conservation of mass. The total volume in the domain must always be the same. But that is not always true when we use numerical model. Numerical models tends to break this conservative property because of the numerical diffusion, because of the cutoff technique that we use. So a good model will not will reduce or will minimize the loss of volume during the simulation. So conservative property is a very important property that we want to have in our numerical model. So this is the volume changes in our numerical model after 1 second. For this very drastic surface deformation, the dam break flow with and without obstacle, we can see that from the simulation, the deformation is very drastic. A lot of breaking, a lot of coalescing of these water particles, and it really tests the accuracy of your model. So after 1 second, we found that our model has less than 1% of mass lost. So it's pretty good for this kind of problem because the flow is deforming drastically. In the next part of my presentation today, I'm going to give you a brief explanation on the method that we use to develop our numerical model. So it's going to be a little bit technical, but I'm going to explain it in on the surface, and later maybe if you're interested, you can refer to the technical paper that I will share with you later in my presentation. So our motive is to develop a conservative, as I told you, it should be conservative, oscillationless, so very little numerical oscillation, and a very robust model. That means it not only can work in one problem, but it can work in other problem which has very violent flow. So a robust model. So we need, of course, a conservative momentum solver, an accurate surface tracking method, and a lot of verification and validation in order to develop a reliable model. So I'm going to explain 3 of these. So momentum solver, in our model, we use the VSIAM3 method by Xiao. I will touch this in a while. And we enhance it with a temporary moment. You can look at the paper of Yokoi, how he enhanced the model. And tracking surface model, we use the TING scheme. Of course, it's based on VOV. I explained to you the VOV method, but we solve the VOV function using thin skin. And then we verify and validate our model using a dam break flow problem for verification, and we validate it by carrying out a tsunami propagation experiment in our lab. About the VSIAM3 model, it's actually quite complicated to explain in detail, but I'll give you a preview. You can refer to the paper by Xiao 2005. VSIAM3 stands for Volume Surface Integrated Average Multi-Moment Method. Okay, the short form of this acronym. And this model is based on finite volume, and it is highly conservative. It's a highly conservative method to solve the momentum equation. So we cast the momentum and continuity equation in the conservative form like this. We have the advection, the pressure, the shear, the body force, and the continuity equation. In the VSIAM3 model, we redefine the velocity as the surface moment and the volume moment. What does it mean by moment? It's just a name given to the surface integrated average. That means for each of these velocity, we redefine them as surface average. So we have 3 different surfaces. Of course, we have 6 here, but the one that represent the X, Y, Z, there are 3 here. So they are defined as the average of value Q. Q can be U, V, or W, any of the velocity. But these are the definition of SIA on 3 different surfaces. And also VIA. VIA is the volume integrated average for either U, V, and W. So based on this, we also define the pressure at the center and all the SIA and VIA moment. The SIA moment on the surface, VIA moment at the center of the cell. This is called the Mgrid system. Just a name given to for this kind of definition. And then the next part is the algorithm. How do we solve it? I already explained about the method of VSIAM3, the concept, and then we are going to solve the momentum equation based on this method. First, we solve the advection phase of the momentum equation. So we obtain a new value. From an old value of velocity, we obtain a new value. But this is not the final value, so we put a star here. This is called the temporary value of velocity. And then we upgrade the temporary value with the shear stress or the surface stresses, and also the body force. And then we can upgrade the temporary value to another temporary value. So we give it another name, U star star. And then we solve the Poisson equation for the pressure. In order to satisfy continuity equation, we can derive this Poisson equation. So we can get a new pressure field. So this new pressure field will be used to upgrade this velocity. Okay, so we upgrade the velocity using the new pressure that we obtain from the Poisson equation to get a final velocity field. This final velocity field is the solution after one time step. So after one time step, we get a new velocity field, and we use this velocity field to evaluate our F function, the Wolf function that defines the surface configuration. From here, we can get a new value of F, and that is how we evaluate the surface configuration based on the new velocity field after solving momentum equation. The next thing is, after we have developed, we need to check our model by the verification process. So here we use the dam break flow problem. So we compare our model. The bottom one is our model. This is flow 3D, and this is the experiment by Lobowski. We compare the propagation speed of the leading wave. Okay, leading wave means the wave front when it starts to move from the right hand side to the left hand wall. So the speed of the wave So we verify our model speed with the experiment as well as other experiment carried out by other researchers. So this is one way to verify a free surface model. So it seems good, the performance of the model. Another one is we can check the attenuation of depth at the origin. So here, water level will reduce when the flow propagates to the front. So we can check what is the rate of the water receding here. So this is the rate of receding, the water at the origin receding. So we compare it with the experiment as well as the other researchers' results. Also, another important measurement to verify the model is what is the force here at the bottom, at the wall, at the left-hand side wall. We measure the pressure, the hydrodynamic pressure. Is it same with the experiment? So we can compare the model and also the experiment, and we found that the reproduction of the hydrodynamic force on the wall at P1 location, P1 is the location here. So it's pretty good. We can reproduce the, although not 100%, so, but there's a peak close to the experiment observation. And then we have very good result for the sustainable pressure phase here. Okay, after the water hit, more water come here to reach the left-hand side of the wall of the domain, and created this sustainable pressure phase region here. So the results are pretty good. Also, we can check for another location, P2. P2 is slightly higher. The result is even better. We almost tally with the experiment observation. Okay. So this darker line is our model, BSIM plus TM. It has a better result here. The final part is model validation. Okay, we set up an experiment. This is about a 50-meter flume. The middle one is about 30 meter. The part that we use is about 30 meter plus. So we set up a water tank. It's really quite primitive way to do to generate tsunami wave. So we store water in the tank up to a level, and then we release the gate, and the water will come in, and a wave will be created here, and then the wave will propagate to the we created an offshore profile here on the flume, and then we put a model here. Okay, so the for the start, we put a rectangular model, a box here with several pressure sensor at the front of the box and at the back of the box. And this is the sensor at the bottom here, P1, P2, P3, P4. And at the back of the box, we have P5, P6, and P7. And we put the model here, and we measure the pressure induced by the tsunami wave, the propagating wave. And then we carry out the same simulation using our model. So the top one is our model. The bottom one is using Flow3D, a commercial model. So the biggest difference, just by looking at this by naked eye, is the resolution. You can see that for our model, the resolution is really high. You can see a lot of wave generated on the surface versus the Flow3D model, which is rather, it looks rather calm. The water is very calm and smooth due to the low accuracy. I'm not saying this is not good, it's good, but we developed an even better one. You can see water even over top the surface of the building. I will show it to you that this overtopping of water on the surface is the correct answer. This is what we observe in the experiment. Versus Flow3D result, we cannot see any overtopping of water on the top of the building. And this is the side view. You can see water overtopping the building. And this is what we observe from the experiment. This is the experiment result. This is our model, the middle one. And this is Flow3D model. Just pay attention at time t equals to 1 second, you can see water overtopping the model in the experiment, and we could observe this in our model, but we couldn't observe it using Flow 3D model. So Flow 3D model, the highest accuracy that you can get is only second order, but this is a third order scheme. So it has better performance compared to a second order numerical model. Of course, surface configuration is not adequate. We have to compare the hydrodynamic force. Here we tested with two wave height. One is 40 mm, one is 100 mm. So the 100 mm one is the red one, and we measured I think 10 different points, but I'm going to show you 2 points, P1 and P5. P1 is the point at the bottom facing the wave. P5 is the location behind the box. Okay. So for P1, we can see for both cases, the numerical model could reproduce the peak of the pressure. Okay, and it also can reproduce good sustainable pressure phase here. After the peak, the sustainable pressure phase is well reproduced by the numerical model here, the red line and also the blue line here. This is for 10 mm and this is for 40 mm. Same goes with the pressure at the back of the building. It's pretty good. The reproduction of the result is quite good for the pressure. Next, what we do with our model is, after we have developed the model, we also look at a different scenario where we are going to simulate the interaction of tsunami with a model with gable roof. So this is a photo somebody took at Penang Island when the tsunami wave approaches the coastline. So most of the houses in Malaysia, due to our heavy rain, we receive about 2,500 mm per year of rain. So we need to discharge the water as soon as possible. So we all have this kind of roof design. We call it the gable roof. But gable roof also, in terms of tsunami wave hitting the house, the gable roof is also pose a disadvantage to the structure integrity. So we are going to simulate the interaction between tsunami wave with the gable roof house or gable roof structure. So we carry out this kind of experiment. We are still studying it, and also we actually have produced a paper about this. Maybe later I will show to you. I will share with you. And this is the side view of the model of the wave interacting with a house with gable roof. Okay, we are approaching the end. So what lies ahead of us is the challenges, how we are going to use this model to generate more benefit for our society. So we need, because all the study that we carry out is just for single model and for a very, very simplified problem. So we need to apply this for more complicated problem. So this kind of model is very high in calculation load because it is a full 3D model. It can give you very accurate, very detailed information, but it also causes a very high calculation load. So this is one of the problem with 3D model like this. Also, if we want to integrate with offshore tsunami model, which is totally different, normally they use the average model to predict the arrival of the tsunami to the shoreline. So how we are going to integrate this with the offshore model is also another issue that we have to face in the future to expand the usability of this model. Of course, as I told you earlier, one of the motivation of developing this model is to come up with a better design, not only for the outside of the structure or coastal structure, but also the inside of the coastal structure. For example, one of the students carry out the study on how far you should place a wall inside a house, inside a coastal house. If the wave hit the house, the water will go into the house and it will cause different what they call forces on the wall here. So how are we going to reduce the impact of the tsunami force in case it happened to coastal houses? So we can use numerical simulations such as our model, very detailed model, and we can study very detailed phenomena to improve our structural design. So this is one of the use of our model that in our plan we are planning to do more simulation to help the design of coastal structure. So as I promised you, this is the references that you can refer to if you're interested to know in detail, especially the third paper is all about the development of the model that I told you. The title is Robust and Efficient 3D Model for the hydrodynamic simulation of wave on land. You can find it in Advances in Water Resources. And also some of the experimental investigation on the loading on internal wall. You can find it in this paper, Coastal Engineering. So I hope you benefited from my presentation today. And if you have any question, you can ask me after this. And this is the photo that I found yesterday, a very old photo, about 11 years. We had a dinner, nice dinner in Kyoto with, this is me, by the way, okay? And this is Professor Flores and and his wife. And we had a nice dinner about 11 years ago. We used to be colleagues in Kyoto University, Japan. So thank you for your time. Please do not hesitate if you have any question on this model. Thank you. Back to you
very much.
Flores.
Thank you very much, Dr. Poe. Now we're open to questions. If you have any question, you can leave it in the chat window, or you can raise your hand. While somebody types a question, Dr. Poe, is this code already public? Can it be easily downloaded? Is it available on any
not yet. Actually, yeah, we are planning to make it more user friendly, but at this stage it's very, how to say, very messy code, you see. So we have not reached the standard like open form. You know, there's a very famous code called the open form, which is widely available and also widely established. We haven't got into that stage yet, but maybe that is our ultimate goal, you know, so that everyone can help to improve the code that we develop. But the code now is in infancy, it's a baby stage. So we haven't uploaded it to any of the, you haven't shared it with the public, to say so.
Please share it with us first. As you mentioned at the beginning of your video, we have had several tsunami cases in Peru over the last centuries.
Yes.
So this is a problem that we also need to focus on. We have a question in the chat window. In general, what are the computational demands to run this kind of simulations? Is it necessary to use a parallel computer? Is it necessary to use a computer cluster? What's the demand in computational resources for this?
Okay. For the cases that I have showed to you, let me show to you a few cases here. Okay. For example, this case. Okay, this kind of case is a very simple case. We use a normal Intel i7, I think i5 or i7, to simulate. For this problem, it takes about 3 days to simulate for about 30 seconds. So of course, we did parallelize some part of our code using OpenMP. It's a very simple, just to make the iteration of pressure a little bit faster. But you can, for future, if the model gets more complex, if the domain is bigger, of course, parallelization, very organized parallelization has to be carried out for the calculation to improve its efficiency. But normal desktop, house desktop, if you have time, if you're not very urgent, maybe a few days will do the job. Just my answer to the question.
Thank you. What's the most interesting finding regarding how coastal structure should be designed based on the initial simulations that you have run? They should be farther from the coast. They should be flatter. They should be, I don't know, what are the first findings that you're having after playing with the not playing, but testing your code with different types of structures?
Okay, to be honest with you, I did not carry out the simulation for the next case. It means this case. I'll show to you. The one with the gable roof. Okay, from this part onwards, I did not get involved with the simulation. So because my scope is not to say my scope, I developed this model so that the student could use the model. But for this part, if I have no confidence to answer you what kind of results, what kind of situation, the gable roof, how the gable roof and the tsunami interact, I have no confidence to answer you. I'm sorry. But I think the information is available in the paper that I shared with you just now. So maybe you can take a look at the paper. I'm really sorry, I cannot answer this.
Thank you.
I have another question, Dr. Flores, if you allow me.
Yeah, of course.
First of all, thank you very much for your presentation, Dr. Puay. It was very interesting.
You're welcome.
I'm curious about the marker and cell method you show in the first slide.
Okay.
What is the difference between that method and the one you propose? Because, well, I'm not an expert, but to me, it looked pretty good also. In the first slide you showed in the animations. Is there any big difference between that marker and cell method and the one you propose?
Okay, let me show you the slide for the marker and cell, right? Your question is, what is the difference between the marker and cell method and my method, am I right?
Yes.
So this is the marker and cell method, and this is the method that I propose or I use for my model. Of course, the biggest difference between these two models is the way they represent the surface. Marker and cell, they are using, as you know, marker. It looks like a particle, but we are not tracing the particle. We are actually calculating the velocity domain, and then we evaluate the marker. It's a bit different. It doesn't solve what we call the advection equation for the fluid, such as in the Wolf method. In the Wolf method, we define the cell that contain fluid and doesn't contain fluid. But in marker and cell, we define between cell that contain fluid and doesn't contain fluid based on the location of the marker. If the marker exists, then there is fluid there. But if the marker is not there, so there's no marker. But marker and cell is a pretty. I'm not saying that it is not good, but the calculation load is much higher than the Wolf method. So this is one of the biggest advantage of the Wolf method, and to trace very complicated what they call surface configuration, surface deformation, the Wolf function has been shown to be more superior than the Mg method. For a simple problem, yes, Mg method can be used. So that is my comment. So therefore, we have another problem, which is it looks very similar to Mg method, which is the other method called the MPS method, or this is a Lagrangian method where all the movement of the momentum equation is solved for each particle. There is no cell meshes here. There's no meshes here, no calculation mesh, but we solve the momentum equation for each of the particles here. So this is another method to trace the surface configuration. So it is pretty new, and I think the performance is also very good for this MPS method. This is called the Lagrangian method versus the one that we have just seen. All these are the Eulerian type. Even this is Eulerian type. There is a calculation cell here. Did I answer your question?
Yes. Thank you very much, Dr. Pue.
Thank you for your question.
Okay, do we have any other question? If not, we can thank Dr. Pue for his time, for sharing with us this state-of-the-art research, because you are still working on this, and we're happy to see that it's having really good results compared to the models, the physical models that you have shown, which again means that we can steal it sometime in the future to also start using it to predict behavior of coastal waves in Peru as well. Thank you very much for your time, Dr. Pue, and for waking up early to share some time with us.
My pleasure to share with you.
So to everybody else, thank you very much for your participation today. We once again are very happy that we have had Dr. Pue with us sharing his work on this. This is another area of civil engineering that needs to be further developed in Peru. I hope some of our students who I see here can choose to decide to work on these topics. You know where you can contact a specialist on this. So thank you everybody for your participation as well, for being with us here. And before everybody leaves, I will present the next event that we're going to have on this series of webinars in civil engineering. We're going to have next week commemorating 10 years of the earthquake and tsunami in Japan. We're going to have Dr. Takeshi Katsumi, also from Kyoto University. He was also a former colleague of mine, who is going to talk about, we're going to focus on geotechniques and geoenvironmental engineering and the recovering of soil materials from disaster debris from 2011 earthquake of Japan. So once again, thank you very much, everybody, for your time, for being here with us today at this time of the day. And once again, Dr. Pue, thank you very much for your time. Thanks, everybody.
Thank you.
See you next week.
Thank you. Bye.